roughly that is the number. Fortunately or unfortunately, we can select 6 colors. 6 colors. It was ultra short, but with or even 5 because we have to identify the other one. The other yes. Okay. The equal 8 correspond to 600 million years after the Big Bang. So, yeah. Yeah. Okay. So this is very generic title because the title says what we can learn from gamma ray bursts. This is generic because I'm considering let's say three different topics. The first one is the classification of GRBs in 7 different subclasses. Then there is also the possibility to estimate from the definition of these subclasses the rates of occurrence of such subclasses. And from them to infer some consideration, some expectation from the gravitational wave emission, but I don't know if you heard already from the program. And then if there is time and if you want to listen this other topic, there is the possibility to use GRBs also for cosmology, I mean, to do infer some constraints from the cosmological parameters. So without losing time, I'm speaking today on behalf of this large collaboration, so it's not only my work. So let's start with the first topic, let's say GRB classification. Okay, so I start here using the ICRANet diagram because it's a very useful tool and was used in the past to discriminate between short burst and long burst. This is what was done up to 2011, if I remember correctly, even 2015, following the work by Calderone et al. So as you can see here, short GRB usually identified as short GRB less than 2 seconds. And long GRBs are identified with sources lasting more than 2 seconds. So initially this classification was seen here in this CPKI diagram through 2 different correlations. The multi-relation for long GRBs that you can see here, and this new correlation called the Lagrange correlation for short GRB, which is let's say a compilation of short GRBs used from identified within this group and the other ones identified in this work by standard type. So, and then eventually there was this possible other family of GRB called X-ray flashes, which you can see here on this work, the definition for the definition of this class of GRBs, which are softer, mainly they peak energy, the peak energy of the spectra are softer than the ones of these other long bursts. And this was let's say, the state of the art before, let's say, our work. So there were three different classes, and this classification was mainly based from information in gamma rays. But the question is what we can infer from other energy bands, for instance. And the answer can be the following. For example, let's consider the GV emission, where GV emission is the let's say energy emitted by source in this energy band 100 MeV, 100 GeV. As you can see here, plotting these two nice diagrams here, the light isotropic energy, LAP is the instrument on board in detecting this high energy emission, versus the isotropic energy of the GeV gamma rays. And these are the ones, the LAP fluence in this energy range 0.01, 100 GeV, and the GBM fluence in 10, 1000 GeV, you can see that there is a kind of distribution for sources like these ones and these ones, where the squares are very energetic long GeVs with energy larger than 10 to 50 watts, so this line shift perfectly. And also in this case here, these are long GeVs with isotropic energy larger than 10 to 50 watts. These diamonds, the blue diamonds, instead are short GeVs with isotropic energy larger than 10 to 50 watts, and so on here. The triangles here are long GeVs with the energy lower than 10 to 50 watts, and these are short GeVs with energy lower than 10 to 50 watts. As you can see here, okay, forget this line is shifted, it should be here. Below the 10 to 52 limit, we have only upper limits for the GV detection, GV energy or emission or detection. Namely, sources below this value of the isotropic energy do not have GV emission. While, on the other hand, short GeVs and long GeVs with energy higher than 10 to 50 watts exhibit when they are inside the instrument field of view, LAP field of view. And this also in this plot, you can see that usually long and short GeVs with energy lower than 10 to 50 watts do not correlate, do not show any kind of correlation or presence of this GV energy emission. So, this was the plot showing that only sources, these plots show that only sources long and short GeVs with energy larger than 10 to 50 watts exhibit high energy emission constraint. Energy. Okay, I repeat, these ones are long GeVs, energetic ones, let's say, and these are short GeVs, energetic ones. And you can see also here, this is a long GeV. Below, instead, is another correlation showing the fluence in the LAP between this and in this energy band, and the fluence in the GBM in this energy range here. So also to show that these sources, the energetic one, have a correlation linking each other, let's say, the gamma rays and the GV emission. But this correlation is not found for the long and short GeVs with energy lower than 10 to 50 watts. So this was asked by a referee just to show that actually burst with energy lower than 10 to 50 watts. Okay, we can stick to the first one. Exactly. Affluence. I prefer to start. Yes, I prefer to start with the observational evidence and then to move into our theoretical classification, because this is the best and the more effective way to show that there is a division of classes starting from the data, and then from the data we can infer the different classes using the theoretical paradigms we developed. Okay, and here you can see this one long. short GRBs, which have the more stringent one, the more stringent power law. Yes, yes, I will go into. Yeah, just the name, because here there is the energy, so you can show. Okay. Okay. Okay, no problem. Yes, okay. Okay. In fact, on this purpose, these luminosity light curves in the rest frame of 100 GeV here is highlighted in black, just to say that these are luminosity light curves of long GeVs with energy larger than 1052 Hz. Yes, okay. And they reflect this. Okay, right. Okay, to catch the attention. And so, for the same reason, these are the short GeVs with energy larger than 1052 Hz, and this is the luminosity. These are the luminosity light curves in the red frame energy band 100 GeV. And as you can see here, in the case of short GeVs, there is a very constrained, very narrow correlation with time with this log E up to minus 1.29, which gives more coverage here.
No, the spectacular result is that as soon as the black hole is full, you generate jet. Generate and it's very, very energetic. And all of them follow in the case of two neutron stars, okay? Of two neutron stars, very then there's a behavior which is identical. So all of them means that the black hole is standing. That is therefore, no matter the clinical start before the contact. And if you have a low dose, again, don't worry about the small change. But again, they follow a general score, which is the same. The only difference is that in the case of the neutron star, the system is much cleaner. Therefore, we have a real universal law. Yeah. Because it is very difficult matter. Because in order to be a real supernova, there is some difference in the beginning. But as soon as the time scale is gone, characterized only by the capital. We see because we are trying to find a way to try to change the data.
No, this one you mean?
This is the luminosity as a function of time. They evolve in the same law. Exactly the same. And that's the light over the period of the gamma ray burst. Yes. And between 1 second, imagine if we are talking about the fraction of the tenth of a second from the tornado, and which immediately gets that over. And then, carefully, 4 or 5 or 6 different. Yes, yes, yes. But they are the same machine. They are completely different distance. Completely different. Different Z is what we alter the data. Now the thing is here. They're completely different objects. But once you normalize, yes, by the distance, you put especially for you,
it is also K corrected. Also K corrected.
it's clear that people basically the plan for thinking about five together. Think about all that happens except to all the things. And if they don't have enough mass, then it's all yeah, when you have short gamma value flash, but if they go over the almost all of them, in all of them about one, you have general evolution starting. I mean, it seems terrible. I mean, there is one point I would like to mention. But there is another point. From the theory, we can say that when the twists are met and they have enough mass to form a black hole, they usually will form a black hole with roughly the same spin. Exactly. Which is another point. Exactly. No. I no, it's the form. That when the two neutrals are, she's four. But this theory then show you that no matter the different masses, you always have similar temperature parameters. Sometimes it can happen that the aerogram was smaller, and this may be this case in the beginning, whatever. But what you go in, then it's universal. And the just again, you give up the one that after that, the order of the almost maximum. Yes, that goes further and larger. By the time it goes to the hole, you get the halo. More than yes. And then you can get down to one. Exactly. But here is the point. What is the point? We did it. Dopo degli dicevo per informare. Observation. If this parameter I is bigger than 10, here, the material that the creating cannot get down to the appropriate horizon because it's physical. You get the generating dimensions of velocity and radius and time, and the arm is too big. So, in order to become a black hole, it's got to get rid of the angle if it's a black hole. It's an end. So it's got to eliminate it. What I know I didn't realize was that what two orbital bodies are, if you were to calculate the impact, then it's not a black hole. The angular momentum is bigger. That would be when I find that.
But people that after when you get it's time, it's always one.
Yeah.
And it's very one, and then you keep going the same way. This is the reason why all of them are the same way. Yeah, it's fantastic. I mean, if it was not the uniqueness of the care, if there was no uniqueness of the care, everyone they will be here. And then we're just attention to all the people around. Now, what is very interesting is that in the most complicated achievement of clearly that you have a supernova actually, but it's not so clear. It's not unique. And the mass capacity which asymptotically okay? That is at the novelty of it. If every one of the please participate in putting the color into the result. And very likely you can make a special that there is too much material. You have to I mean, if you look at all them together, without taking into account that the energy that we came and therefore the diagram which we should do is this one. Okay, they need to be okay. So they can be wrong, but they do not correct. Okay, this is the reason why I'm insisting to put the one before and the one with the K correction and the time correction. We have to show that how one communicates that. That's not easy. It was crazy for me to see it.
There is a question. This can be included in the rate estimate. Okay. Yeah.
Now, you are asking, we are speaking about the data request. Now, knowing the right truth, just let's see what show. You are asking,
No, okay. Avete fatto un
but
sacco di
there are
spoiler.
two different families. Okay? Wait, there are two different families. They are short security and long security. The short security comes from neutron stars. Okay? The neutron stars are processed stars. Second, third, fourth generation. Okay? The rate of star formation correlates to the long term, not to the short term. Because the short term are random. The star formation is correlated to this. Now, if you have pressure, it's a long term. So, it's a very long. Therefore, that's the period.
Just a comment that this fact of the star formation rate is very important. But okay, there are still debate on the shape this star formation rate. Sometimes there are different joint power laws. Sometimes there is no agreement. But as I will show you later, you have to include this, let's say, this history of the formation of, let's say, long and short GLBs. Depends on different models. But if you use or if you don't use, namely, if you assume a constant function equal to 1 everywhere, it doesn't make any big difference in the estimate of these rates for the moment, because we are not in the position to be so precise to give some very narrow constraint. Yeah, yeah.
Okay. So much for the first.
So at this point, I should insert writing saying alert, spoiler alert here, because spoilers alert, anticipazioni. Ne avete messo troppo, non c'ho più niente da dire. I have nothing to say more. No, because you said everything concerning the progenitors, concerning the different fruits of classes. Okay, let's repeat. Okay, the next slide is yes, yes. No, of course not. No, I understand. So after, okay, the point, just to summarize, the point was, this was the starting point. And then we made some considerations in different energy bands, not considering only gamma rays, but considering, as you saw here, the GVA radiation. But we can draw some conclusions also using the X-ray emission. Because there are different behaviors in the X-ray emission, both for short and long GVAs. Here I draw the separatrix, this line of 10 to 52 Earth, just to recall that in the case of short bursts, you can see that there are some set of X-ray after the emission. In the case of these sources, short bursts with energy lower than 10 to 52 Earth, you have this compilation of X-ray afterwards, not showing anything particular, not showing common behaviors, nothing in common, let's say. In the case of short bursts with energy larger than 10 to 52 Earth, you have only one example for the moment, and only upper limits, late upper limits for other sources. So for these short bursts, let's say subclasses, you don't have something to say about. But when you go to long bursts, you can appreciate that there is a huge difference when you consider long GRBs with energy lower than 10 to 52 Earth and the ones with energy larger than 10 to 52 Earth. For the lower one, for the less energetic ones, you don't have any particular common behavior in the X-rays. While when you go to the high energetic GRBs, rather than 10 to 52 Earth, you have this late common power law behavior in the X-rays. Again, also in this case, these are luminosity light curves. It means that we just computed the luminosity in a common rest frame energy band 03 MTV for all the sources, and we just follow the evolution of this light curve through the time, rest frame time. So you can see that late time there is a common behavior, and this is the law which rules this late common power law behavior. So as you can see here, there is a huge distinction, at least for long bursts in the
we have seen before different APIs, how long they last, the short and the long. And we have seen that in the family of the long, in the family of the long, in energy larger than 10 to 52, there is the gas capital. The gas really from what we discussed. And it's not come from the center. But let's see what happens. What happens in that time after the first 100 seconds of the journey. After the 100 seconds, the GRB keeps working. Okay? It keeps working for up to 10 to the 6 seconds, which means 10 to the 6 seconds is 1 month. Okay? For 1 month. Now, what is very interesting is that during this 1 month, there is some feature which distinguish the two, the one which has a common, one which don't have a common. In particular, the one which don't have at all, there is no special feature.
and they lose energy, but there is no special feature. This one was certified for it's made up. We understand why they do that. This one, again, we understand why they do that, but it's just fundamental physics because of the evolution that goes down. Very important. Okay? But there is no signature. Instead, when we take the long one, where there is a black hole, there is a signature. There is a constant that when we call the field, the more energetic it starts to be stable before, the less energetic it starts to plateau, it's a market disorder. There is a general wave which starts from here, and then they join together in a standard way. We never actually take them from together. In all that field, if you look to see what the crystal was when the energy was generated, it's generated by two bodies which have not and now they're pouring out energy, but one with the other part of the lake, they what we think is because the color form but today you see all the formation of the black hole. Now the black hole is there, still generates energy by rotation, so but there is a long-term product. Then there is another activity, one of the people that there are many different forces. One new forces which start is that you are an additional in this system. In which you are very long to and it originates from the supernova singularity. In different phenomena, that after 100 seconds, lasting for 1 year, but nothing to do with before this system. This is after the black after the gamma ray is what is called the afterglow. And there is a fundamental difference between what is an after from doing and before and after. After 100 seconds, for the one which has a hole inside and the other one which don't have a vacuum. And in particular, this feature is the one that when we study, tell us something about the interaction of the gamma ray with the supernova. We will consider the gamma detection to the possibility of the fundamental step. It's difficult to go far, too much farther. But maybe we stop at this time, and let's stop at this time. We will discuss it together. Let me see in the minutes the next time.
Yeah, actually here you can appreciate that there is a moment of four subclasses of GRBs, 2 for short bursts and 2 for long bursts. This was from the data to say that we can arrive at this point at the moment where you have these two subclasses of short GLB, one we named short gamma reflectors, which are the short bursts with energy lower than 10 to 52, which are softer than the authentic short GLBs, mm-hmm. Mm-hmm. Okay, I cannot play it. Okay. It's longer because at that moment when I did the list of sources, I didn't include the duration because I didn't know that this one was one of the goals. Because the goal was simply to update the number. So I have to put also the duration. Okay, rest frame. And also it's not so clear because some sources which seems to be short actually are not short. Because if you just correct the redshift, eventually you have some sources which are borderline, which last 1 second, but actually they are not short. Because if you look at the energy, if you look at the EP,
And I asked you to do a cross exactly the old way and the new way.
Mm-hmm.
And what you have done is that you need to decide the context right before you find the advantage.
This is yeah, my point was just if since they are distribution, necessary there is one overlap. Just and we have to make it. Mm-hmm.
Well, really got out, but right before people had to figure out
Okay.
when you get short,
Totally apart. Okay, okay, this was just to say we have four at the moment four. Appreciated. Yeah, but because after introducing the prolonged GeoBit X-ray flashes in BDHN, I was entering the details, showing that the progenitor is a binary system composed of a carbon-oxygen core and a neutron star companion, depending on the, let's say, depending on the binary separation and the amount of mass created and the mass of the neutron star, you can have two different possibilities. X-ray flashes, where after the interaction you have a massive neutron star and a neutron star formed out of the carbon-oxygen core, and a binary-driven hypernova, which form eventually after the interaction of the neutron star and the carbon-oxygen core and so on. You said already, so this was the philosophy, let's say. So I think the comparison was just to show that they have episode 1 in both the cases. So thermal component in the beginning of the gamma ray light curves. This is for an X-ray flash, so 60218. This is for a BDHN, which is the prototype 90618, the Indian source. So you can appreciate different radii and temperature just because this system has is characterized by a larger accretion region in this case. Instead, in BDHN, this region seems to be narrower because the radius is between 10 to 9 and 10 to 10 centimeters. White here was 10 to 12, and the temperature is higher because it's more compact. Then episode 2, there is only in the case of binary-driven hypernovae. So for the sources with energy larger than 10 to 52 Earth, you have episode 1, and after this there is the black hole, the formation of black hole and the emission of the gamma ray simulated within the Fire-Sheen model. For X-ray flash, you don't have it because you don't form a black hole. So you have only episode 1. I'm going faster because you said before. Then there was the comparison between the X-ray flare plateau after the phase. So in X-ray flashes, you don't have any flare, initial flare. There are smooth structures here, which can be still the continuation of the episode 1 phase. No special features in the late X-ray afterglow. Instead, in the binary-driven hypernova, you have this common behavior. Here, this is the power law with the time, and the nesting, what you were saying before. Namely that this part of the light curve, X-ray light curves, are characterized by a plateau phase and the late power law. Here, the jet emission, which arises only for binary-driven hypernova, is never observed in X-ray flashes, even though they were in the lab field of view. So we can conclude that in the induced gravitational collapse paradigm, this emission correlates with the black hole formation because it's observed only in the systems which form black holes. This is, was an insight just to spend some words about the FTA phase in binary-driven hypernova, namely that you have this, in binary-driven hypernova you have this initial flare after the end of the confirmation phase, a plateau, and the late power law decay, which was shown before. And the study of this flare, I don't know if you want to continue to say this, so I can skip it. It's okay. So only in this flare there is a thermal component. Yeah. Now in the merger paradigm you have these short gamma ray flashes, which are sources with energy, isotropic energy lower than 10 to 52 Earth, and authentic short GeoBits on the right side, with energy larger than 10 to 52 Earth. I can go on. I put here the picture. Okay, remember this picture about the galactic binary with the total mass of the binaries. You can see that there are cases in which, depending on the value of the neutron star critical mass, you have systems which form black hole, which have some of the mass larger than the Earth. Gamma rays, also in this case. X-ray emission was a comparison also in this case. And the GV emission, of course, which is present on the case where a black hole is formed, and not in the case where only a massive neutron star is formed out. This is the 10 to 52 energy lower limit in the binary system. Then the gamma ray flashes introduce the other families, the other missing families. because we have also another family, the gamma ray flashes, which are namely hybrid sources, which have both properties related to short GBs, for instance, an initial spike-like emission with a hard spectrum, but they have also a softer play with the lower with the softer spectrum in this case. And if you see the total duration, they have a duration larger than 2 seconds. So in principle, they should be classified in the old fashion like long GRBs. But they have these hybrid properties, and so in our understanding, since these sources do not have an associated supernova, like in the case of 06-0614, which was ruled out by Massimo della Valle, who showed that if a supernova would be associated with burst, it should have been 100 times less bright than the usual ones. Yeah. So for this reason, there is this part which is typical for short GRBs. This part is characterized by the fact that we have in our model a more baryon contaminated environment, a progenitor, let's say not progenitor, let's say. We conclude that these sources can be very likely the merger of a wide open and neutron stars. So two compact objects, but with more baryon load. More baryon load. And eventually the fate of this will be a massive neutron star. Then we have also a theoretical, for the moment, a theoretical subclass called ultra-short GRBs, and they originate from the neutron star black hole mergers, as you can see here. I'm sorry. As you can appreciate from here, this class can very likely arise from the outstates of the binary-driven hypernova, which are called black hole neutron stars. And there is also this possible class of black hole supernovae, where you have a very peculiar VHN, in which you have a carbon-oxygen core, which has in the vicinity in the binary system not a neutron star, but an already formed black hole, like in the case of Cygnus X1. So with this we have 7 subclasses. Okay. And so this is updated with the classes we have identified. We don't have yet identifications, but we are doing this for black hole supernova, which should be here, around here. We don't have ultra-short GRBs because we don't have still observational evidence, but we can update here the gamma ray flashes, especially when you consider the first initial spike-like emission, which is very hard and correlate, and it is in the correlation for short gamma ray flashes. Then the rates. Okay, if you follow, I don't go into detail. If you follow this reference here, you can compute the rates for the difference of classes of GRBs, and you have here the results. And here, just to reply to Camillo, that here we didn't consider any star formation history because we don't have constraints or type constraints in them. Here, these works were considered. So if you compare, for instance, X-ray flash with the ones in literature, they are the same practically, the rates within the error bar. So including this effect doesn't make so big difference for the moment. Binary-driven hypernovae correspond more or less to the majority of long bursts considered in the literature, and the rate is consistent with the one of the literature. Short gamma ray flash are the ones which are considered in literature short GRBs, so these rates are similar. The identical short GRBs are just a subclass of the total set considered in the literature, so the rate is very low, and the new one is the one of short gamma ray flashes, which is not considered in the literature. Okay, I can skip. This is eventually the most important conclusion for this first part. So you start with different progenitors, you let them evolve, and eventually you end up with these outstates or final configurations, like for instance in long GRBs, neutron star, neutron sub-black hole, neutron sub-black hole again. And this one could be the seed, can be recycled, can be the instates of other classes of bursts, in particular short GRBs, because you can have starting point neutron star binary systems, neutron sub-black hole, and in some cases even exotic. Okay, this was done probably by Jorge in Nice. Jorge, you did it, yes? No? Okay, so simply very fast, we just use the GRB rates and assume this that the electromagnetic history doesn't, let's say, doesn't change that much. It's just a perturbation of the gravitational evolution of the systems, especially for compact objects like neutron star, neutron star, black hole. We can draw some conclusions on the expected number of events detected by advanced LIGO now and in the future with the improvement of the sensitivity. And just this, Jorge can tell that practically systems which can be very likely detected within the advanced LIGO sensitivity can be black hole neutron stars, systems in particular with massive black holes of the order of 10 solar masses. Is it okay, Jorge? No, this one was the new part. I'm working with Luca Itz and Massimo Della Valle, so cosmology will block the one burst. Namely, I can go fast. I skip all this part because this is just a review. Just correlation that you use in the literature, like the Pitt-Price relation, Amati relation, Dainotti relation, Margutti and Bernardini relation, try to do cosmology. All of them are good, but they suffer some systematics and some circularity problems because we use quantities which are cosmology dependent. And I simply arrived to this point, which is the new relation we proposed with Luca Izzo and Massimo Della Valle and Lorenzo Amati. I forgot to put Lorenzo Amati also in the list. Namely, we combine two relations, which is the Amati relation, the Margutti-Bernardini relation. We combined all together to avoid the use of the isotropic energy of GRBs, because isotropic energy is a cosmology-dependent quantity, because it depends on the cosmology you input inside. We use this formulation of the X-ray after we used in the paper of the BHN. You remember this function used to describe the plateau and the late power law decay, the one in the nesting, you remember. We use this formulation, consider that this energy in the X-rays, which Bernardini and Margutti consider, is only this part here, the plateau and late phase decay. We use this phenomenological formulation, we insert everything inside, and eventually we get this relation that the luminosity of the plateau phase is related to the peak of the prompt emission phase, the duration of the plateau, and the late power law decay index. And you can put in a logarithmic fashion, and this is the relation we use. Yeah, this is the advantage that we can calibrate this correlation simply using a subset of sources with the same redshift. Same redshift means that you can take out the luminosity distance dependence because it's the same for sources which have the same redshift. And you can plot a relation which relate the quantities observed in the respective peak, the duration of the plateau and the slope of the late power law phase, but here we consider only the flux because these sources have the same distance, so you can overcome, you can take out the distance factor. We just calibrate the slope of this function. We use this power law. We use the nearest GRB in our sample to calibrate with supernovae the A parameter of the relation, namely the value of the relation to 0. And we obtain, these are the results. I'm going fast, I don't know which is not so clear, but we use all this machinery, all this calibration just to get some constraint to construct the Hubble diagram from GRBs, which is this one, and use it to infer the cosmological parameters for GRB only, which is the case, and gives an omega m of 0.29 in the case of a flat universe, and when we combine with other probes like supernovae, baryonic oscillation, CMB, we get eventually now we're constrained on the cosmological parameter, the mass density parameter, which is this one. And for the future, we are doing the same, enlarging the set of GRBs, and so these are preliminary. You can get lower, narrower contour plots and narrower constraints on the parameter mass density parameter, also testing other possibilities, for instance, a different phase from the last cosmological constant, and also we are going to see if it's possible to track the evolution of the dark energy term using GRBs, because GRBs, unlikely the supernovae, can go beyond the Z 1.7 up to 1.3. So that's very fast. So the conclusions are that the rates. No.
I don't want to see this anywhere because we are even discussing right now about the separation of the seven parts. If you want to do a paper of one or a family, you're welcome. But that cannot be able to start at the time.
Just a small comment. More comment. It's not that we are we are considered two families, but they originate from the same progenitor we are considering, namely in the case of Longevis, carbon-oxygen, or star. So the progenitor is the same. The progenitor is the same for Longevis in the picture of the induced gravitational collapse. So you see, it is true that we have two different classes, but the progenitor is the same. So what we are saying is that if you use the class of GBs with the same progenitor, can work this
very possible because we know very well that the one we check the black hole, one of these alpha, because for a new paper, whatever thing you want to do, you have to recognize this other. Take away everybody else.
Okay.
Okay? It's clear.
Yes, yes, precisely.